What's a vector? Let's start off with an example. Let's say you're walking one day from home to school. Let's put school over here, okay? You'd like to walk straight from home to school because that's the shortest distance, obviously, but let's pretend there's a lake in the way. Here's a lake in the way. We'll call that lake. So in order to get from home to school, you actually need to follow a path that looks something like this. Let's pretend that this is, 700 meters, and let's pretend that this is 500 meters. So we can clearly say that the total distance traveled is 1,200 meters. But you're curious, what's the straight distance between home and school? If we're just stuck with the 700 meters and the 500 meters as a description, we don't have enough information to figure out what that direct distance is. These values that we have here we call scalars. And a scalar is the numbers you're used to seeing. So these are all scalars. Essentially what scalars have is they just have a magnitude. And a magnitude just means an amount, right? So 700 meters is a magnitude. 500 meters is a magnitude. Now, if we wanted a better description of, how to get from home to school or the direct distance, what we need to do is we need to include something else. We need to include the directions. Because if I describe this as a direction, 700 meters, let's say that's north, and then this 500 meters, instead of just 500 meters, if we actually describe this as 700 meters to the west, which looks like the direction that it's going, now we have a better sense of sort of the directions that we're going and the final direction from home to the school, the direct distance from home to the school. So these are no longer scalars because they have more than just a magnitude now. So I'm going to cross that out. These are now what we call vectors. Vectors have a magnitude as well, so 700 meters or 500 meters. They have a magnitude. But they also have a direction, right? Okay, so if it has a magnitude and a direction, then it's a vector. So now if we wanted to figure out what the straight distance from home to school is, it's now basically a geometry problem, right? We can analyze this as a triangle. We need to basically find the direction here, or the distance here and the direction you would need to travel to go directly there. These are very applicable to physics and a lot of the other sciences. So as we saw in the previous, the example we just talked about, vectors can be represented as arrows, right? It's like the direction from one place to another place. So for example, if we wanted to do the vector that went from A to B in this example, A to B is a vector that start at A, go to B, and we represent that as an arrow, like that. We call that arrow AB with an arrow on top. The arrow on top is just a way of representing or letting people know that this is a vector with a direction. So in Google, unfortunately, I'm not able to put the arrow above the letters. So you'll see it just has a bar on top. Really what that bar on top means is AB with an arrow on top. Okay, so that goes for all these questions. Those are actually little arrows on top to represent these things are vectors. So if we're looking for a vector equivalent to AB, AB is the vector that goes from A to B. What's another vector that has the same magnitude and direction? Remember, those are the two things that are important for a vector. I'm actually going to write those down. So a vector, I'll just copy that out here, has a magnitude and a direction. So if we're looking for a vector equivalent to AB, this vector right here, we're essentially looking for one that has a same magnitude, and the way that it's represented is a length. So which vector has the same length as AB and is going in the same direction? So think about it for a second. What vector here, could we make another vector that has the same direction and the same length? And this looks like a parallelogram. I think we can assume it's a parallelogram. So if you look DC down here if we did an arrow there, it would look like it's the same thing, right? I can move that vector DC on top of AB and it would look like it's the exact same vector. So an equivalent to AB would be DC with the arrow on top. What will be an equivalent to CB? Let's do that in a different color. So CB is the vector that starts at C and goes to B. So this would be CB. Notice when I do the arrow, sometimes I just do a little half arrow like that just to make it quicker to do. So what's another vector that would have the same magnitude and direction as CB? And the answer is DA, right? This would be the same vector. It's the same direction, and it has the same length, right? It doesn't matter that they're actually in different physical locations as long as the direction and the magnitude are the same. So let's put that in here. DA is the equivalent vector. What's an equivalent vector to negative AB? Well, a negative vector, maybe you can guess what that is. A negative vector just goes in the opposite direction. So negative AB, if AB looks like this, it goes from A to B, then negative AB goes in the opposite direction. It's just the flipped version of that. So I'm going to draw it sort of beside here. It's going to be essentially going this way, right? It's the vector that goes the opposite direction, negative AB. So which vector sort of matches that? And what I can actually do on this program is I can copy that and I can sort of move it around. What matches up with this negative AB? Well, one answer is this matches up with BA, right? We're starting at B and we're going to A. So that could be an answer. We could also go down here and see that CD is a vector that has the same magnitude and same direction, right? So that's actually two answers there that we could potentially use. So I'm going to do that BA as an answer, or CD as an answer, right? As going the opposite direction. And what is a vector equivalent to AC? Do we have any more colors? Yeah, let's use yellow here. AC is this vector that goes down like that, right? You'll notice if I grab AC here, if I select it and move it around, are there any other places that we can create an AC vector, a vector with the same length and direction as that? And no, that's not really, because none of the other vectors go in that same direction, right? So really, this is AC down here. I'll just leave that there for a second. There are none, right? There's no other vectors, single vectors that we can do that. Later, we'll see how we can combine vectors to do that. But in this case, really, there's nothing that'll give us that, no single vector that'll give us that. So we've talked about vectors having a magnitude and direction. There are a few different ways to represent vectors, and that's what we're going to get to here. So let's start off with this first vector over here. This vector is D. We're calling it D equals 25 miles. Notice how it doesn't have the little arrow on top of the D, and I think that's because it's just referring to the length of that line. Or in other words, the magnitude of the vector. It isn't referring to the direction. The direction they wrote down here separately. So how can we combine those two things into an actual vector, or a description of a vector? Let's start off with just a north, south, east, west. North, south, west, east. Because that's going to sort of be a good way to describe it. We're usually going to do this, north, south, east, west, when we're describing the direction. Because in this example here, the 60 degrees, you'll notice that's 60 degrees from west, right? So the way we describe this vector is we would call it D with the arrow on top because it's a vector, is 25 miles, and then the direction we always put in square brackets. And the direction, it's like we started going west, but then we ended up going 60 degrees north. So it's like we're starting off in the west direction, and then we're changing that direction by 60 degrees north. That's how we describe the direction there. So this now is a whole vector, which is why we have the arrow up here. So that's one way to describe a vector, and that is with magnitude and direction. So this, again, this is the magnitude of the vector, or the length of it, and this is the direction. So that's one way to describe a vector. And if you've taken any physics classes or anything like that, that's probably the one that you've used. There's another way to describe a vector. This is a vector that goes from A to B, so the vector probably should be called AB. Now, this one, it's a little bit of a pain to find the direction in terms of a degree. So instead, we can describe the vector in terms of its change in x and its change in y, right? So essentially what this is the x part of the vector, and this is the y part of the vector, right? If we call this the x-axis and the y-axis. So in order to describe a vector, one way we can do that, so this is going to be called vector AB with the arrow on top. We can describe it like this, having an x and a y part. So in this case, in the example AB, the x part is 6 and the y part is 4. So that's one way we can describe this vector. It has an x part of 6 and a y part of 4. You'll notice how the magnitude, the actual length of the vector, isn't included in here. Neither is the angle, right, as the direction, but it essentially, you can use the 6 and the 4 to come up with those two things. So this is another way to fully describe a vector. So that's the second way, and we call this way, this specifically when we have the square brackets like this, we call this matrix notation for a vector. Okay, there are other ways to represent it. You might see in your textbook, you might actually see people write it like this, AB equals 6, 4. The problem with this is it looks like a point. Now you know it's not a point because it's got the little arrow on top. It's actually a vector. That's why I like using the matrix notation. Another one you sometimes see is instead of having the brackets like that, you might see just regular parentheses here, or you might see instead of this, you might see it like this. 6, 4. Where they're sort of brackets, but they're sort of like bent brackets. And that's just to illustrate the fact that it's a vector. So you might see any of these different ways, but they all essentially mean the same thing. It's like the x part and the y part. Now, vectors, the nice thing about expressing vectors this way is that you're not limited to 2 dimensions, right? In this case, we have x, y, and z. We have a 3-dimensional vector, so an arrow in 3D. And we can easily write that if we call this, well, there's nothing describing this. We'll call this point A out here. And we call the origin here where it starts O. So this vector would be OA, right, because it goes from O to A. And if it's in 3D space, we're going to have a z, x, a y, and a z part. So this vector, in this case, if you look at this graph, think about this coming out of the page, right? On the x-axis, we've gone 5 units. So the x part is going to be 5. The y part, if you look on the y-axis, it goes up to 8. And on the z-axis, it goes to 3. So that's how we could describe a 3D vector using matrix notation. So going back to 2 dimensions here, let's do some practice. How can we describe these vectors using magnitude and direction as well as components? Or we should call that matrix notation. We'll call it matrix notation. We will refer to those parts, the x part and the y part, as components, which is why it's called components as well. But let's not worry about that right now. So for the matrix, well, actually, let's start off with the magnitude and direction of A, because that's pretty straightforward. So it actually says in this question here that 1 block is equal to 1 kilometer. So let's pretend this is like looking at a map from above, and we're trying to represent distances traveled on a map. We're also given compass, that it's north, south, east, west. So A, we know is going north, and if we count the spaces, 1, 2, 3, 4, we've gone 4 kilometers north. Okay, that's A. That's the magnitude and direction way to put it. If we wanted to put it in matrix form, remember we're looking for the x and the y part of it, or the x and the y components. And if you think about it, we're starting here. Are we going anywhere in the x direction? No, right? So there is no x component. The x component is actually 0. But we're going up 4, 1, 2, 3, 4, 4 in the y direction. So think of this as like a map of how to get from the start to the end of that arrow. B if we look at B here, B is just going 2 spaces to the right, or 2 kilometers east, right? And to represent that in matrix notation, we can just say, remember it's the x on top and then the y on the bottom. So in the x direction, we've gone 2, and in the y direction, we haven't gone up or down at all. So it's going to be 0. Okay? Moving on with C. C is a little bit more challenging because we don't actually know the length of it. We know it goes 1, 2, 3, 4, 5, 6 in this direction. So if we look at it like that, it's like we're going 6 in the x direction. And it's actually, we consider positive and negatives here. So I actually didn't define that for the first 2, but usually it's good to define our positive directions. So we're going to say going to the right is positive and going up is positive in the y direction. And this is usually the case. So in this case, to get from the beginning to the end of C, we have to go to the left by 6. So that's going to have an x component of negative 6. And then we're going to go down by 3. So y component of negative 3. So to express this one in matrix form, it's actually easier in matrix form, right? Because it's going to go negative 6 is the x, and negative 3 is the y. So again, think of this as how to get from the beginning to the end. We're going to have to go left 6 and then down 3. Now to express this in magnitude and direction, it's a little bit more difficult because we don't know the length of this. But you can probably figure out that we can find the length of that pretty easily using the Pythagorean theorem, right? A lot of right angles here. So to find the magnitude of C, or the length of C, what we actually, there's notation for this. If we're just looking for the length of it, think of it as the absolute value of the function, because absolute value is another way of saying distance. So just the length of the arrow C is going to equal the square root of 3 squared plus 6 squared, right? We don't need to worry about the negatives when we're doing Pythagorean theorem because the squareds are going to cancel those out anyways. So if we do this, we end up getting, I'm going to just do it as a decimal, 6.7. About 6.7 kilometers is the magnitude of C. So we know it's going to be 6.7 kilometers. And then we need to find the direction as well. And the direction, we'll find this little theta in here, that angle in there. And again, to do this, we just need to use a little bit of trig. So theta is just going to be arctan of opposite over adjacent, 3 over 6, or negative 3 over negative 6. It doesn't really matter in this case. If we do that in our calculators in degrees, we're going to get 26.6 degrees. Okay, so that angle is 26.6 degrees, and let's think of that in terms of direction, right? This angle is here. Think of it as we started off by going west, and then we went 26.6 degrees to the south. Like we changed it by 26.6 to the south. So the way we'd write it is exactly like that. We started off by going west, and then we changed it by 26.6 degrees south. There we go. So we found our magnitude and direction there. I want you to pause the video here, see if you can figure out D by yourself, and I will put the answer up here shortly. So if you did the calculation, there's the answer. The matrix notation, it's 6, 1. Those are the x and the y parts of it. And in magnitude and direction, it's 6.08 kilometers east, 9.5 degrees north. And that 9.5 degrees, if you're looking for it, it's this angle in here. It's a pretty small angle. Now, if you went the other way, if you went up and then this way, you might have found this angle here, which is going to be something like, I don't know, 80.5 it looks like, which is fine as well. That wouldn't be east 9.5 degrees north, though. That would be north 9.5 degrees, or sorry, north, let me just write it here. It would be north 80.5 degrees east, right? Because we started off by going north and then we went east. Try to sketch these vectors down here. So it gives you what they are. Try to sketch them yourself and unpause the video and I will put the answers there. There you go. These are rough sketches. The lengths aren't exactly to scale. A is just 2 meters to the east. B is 4.5 meters north. C, this one, the length isn't exact. I didn't measure it, but it's about 3.5 meters, and the 35 degrees is there, right? Because you went west and then 35 degrees north. And then for D, 3 meters of the length is about 3 meters east, 25 degrees south. There you go. One thing I didn't do, which is really bad of me, I didn't actually show a scale, right? Because in this question, we weren't given a scale. So I should say that that one block equals 1 meter, right? Because that's what our question was in meters. And the other thing that I need in a question like this, which I didn't show, is a compass. Just to show the person, reading this answer, what directions, north, south, west, east. Now, these are going to be the directions we usually use, but not all the time. Sometimes they're up, down, left, right. Sometimes we switch the west and east or the north and south, depending on the question. So it's always good to show your compass and your scale for each question like this. One other thing to take note of. Does it matter where these vectors are? So if I take A, for example, and I move it over here, does it change vector A? The answer is no, it doesn't, right? I can move it up here, I can move it over here, I can move it over here. It doesn't actually matter what the location of that vector is. The only thing that actually matters is its direction and its magnitude. So it doesn't matter where you draw them as long as you draw the correct length and the correct direction.